Hi, and welcome again to my Physics Online video lecture series. In today's video, we're going to be talking about work done by or done upon a gas, namely a gas that is either expanding and thus presumably doing work on a system, or contracting, thus having work done upon it by some outside system. For shorthand, I'm going to refer to this as thermodynamic work. We're going to begin the video by recalling the definition for work. So work is force times displacement, or in equation form, work is F dot, call it delta X. All right, so force times displacement gives us work. Furthermore, we know that pressure is defined as essentially average force per unit area. Finally, we know that we can define a volume as a force times, as an area times a distance. So these are sort of like the three background pieces of information. So volume might be area times length, or alternatively, we could say if I have an object whose volume changes, then maybe that volume delta V might be an area times a delta X. And so the diagram that basically goes with that is, imagine that I have, for example, a cylinder, and in the cylinder there's maybe like a piston, and the piston is going to be pushed from one point to another, like this. Then this delta volume, change in volume, would be this delta X distance between where it started and where it ended times the cross-section area of this essentially chamber that it's in. So if this right here has a cross-section area A, then A times delta X would give me delta V, the change in volume. So now we come and put all these together. So to get thermodynamic work, put these things together. What we end up with is essentially that work being force times delta X can be rewritten as simply F delta X in this case, which is pressure times area. That's force times, force is area times pressure, because pressure is force over area, times delta X. And so this right here is, by definition, a change in volume. And so put everything together and you get work is equal to pressure times change in volume. And that's our basic thermodynamic work equation. Now, with that said, there are some kind of built-in assumptions here, especially in an algebra-based course. In order for work to actually be pressure times volume and to use this equation, we have to kind of assume that the pressure remains constant as the volume changes. So since we are assuming that pressure remains constant as volume changes, we're assuming somehow that the volume change is relatively small, essentially. At least if you think of the ideal gas law, you know that pressure and volume are reciprocals of each other. They're inversely proportional. P times V is KB times N times T. And so if these things are all constant, then changing the pressure and changing the volume, if you increase the one, then the other decreases. So you could, in principle, have pressure remaining constant as the volume changes under ideal gas law, but you would basically therefore need to either increase the number of molecules present or increase the temperature. So And in fact, that does to some extent happen. You might increase the volume of the system and maintain constant pressure, and do so by adding more molecules into the system. In actual practice, if you are to do work on a system thermodynamically, you kind of actually end up expecting T and possibly even N to change depending upon how airtight or gas tight your chamber is. Certainly you expect temperature changes, and that's actually going to be a topic for another video. So let's first consider maybe a quick example with this simple assumption of a constant pressure. For our example, we have some gas that is expanding and pushing a circular piston of known radius by known distance, and it's doing so under, let's say, approximately constant pressure. And so what we want to know is how much work is done by the gas in this process. And we know that the work is done by the pressure times the change in volume, P delta V. And that can be written as P times A delta X. So if we come up here and kind of underline what terms we've been given, this right here is my pressure, this 5.5 centimeters is my delta X. We'll need to convert to meters, so we need it in meters. This right here is a radius which can give us an area, and we want that in meters squared. So we come back down to our original equation. This becomes P times pi r squared times delta X, and then we can plug in each of the numbers into this equation now. So 202 kilopascals. I probably should have noted that this needs to be in pascals. So this is 202 times 10 to the 3 pascals times pi times 0.12 meters squared times 0.055 meters. So now we pull out our calculators, we type these in, and we get out a work done. What we get is 502.6045. So let's round that to, let's say, 2 significant figures. And in that case, work is 5.0 times 10 to the 2 joules, or 500 joules worth of work has been done. Okay, so this brings us now to the other question that might be asked here, which is, what if the pressure is not actually constant? It's a reasonable question to ask, of course, because we don't necessarily expect the pressure to always remain constant in these processes. It might be approximatable as constant. For example, if I have a cylinder, a gas cylinder, maybe this end is fixed and the cylinder is very long like this, and I have a piston here that I move from this point to, say, this point. The change in volume is so small here compared to the total volume of the cylinder that there is maybe some hope of more or less constant pressure. Even then, it's not going to be constant, but it might be approximatable as constant. However, in many of these processes, this approximation isn't valid. Simplest example that probably most of you have some experience with is if you've ever had to use a hand pump to inflate a basketball or a bicycle tire or what have you. You know that you basically end up having a pumping action in which this piston might move from here as far in as here and back. You know, it's almost the entire length of the pump cylinder, certainly a substantial fraction of it. And so we have a pretty drastic volume change, and therefore we expect a drastic change in the pressure during this work. Now in this case, we're kind of doing the work on the gas, and then we allow the thing to re-expand, and then we do work again. You'll also notice, and this goes back to the first law of thermodynamics, again, topic for another day, that if you use the bicycle pump, the hand pump, for long enough, you'll notice that it heats up quite a bit too. But in today, what we want to focus on is how much work is being done. And so one way of doing that is to draw essentially a process as a little chart with a pressure on one axis and a volume on the other axis. And the area under the curve that this process is undergoing gives us the work done. So under the constant pressure approximation, that volume and pressure area would basically be a rectangle. So this is work equals P delta V constant pressure. So this is our approximation. And essentially, we actually kind of like to draw arrows on these to show what direction is this process occurring in. So this is the gas is expanding. If the arrow pointed the other way, the gas would be contracting. So this is positive work being done by the gas. The other direction would be work being done on the gas, which we might call like negative work. Happily, we can kind of generalize that a little bit by noting that for any given process, there will be some diagram that could be drawn. For example, maybe the pressure versus volume looks like this for a motion. Maybe thereafter, we want to find out how much work has been done. Well, to do that, once again, you find the area. So area equals work. And this even works, no pun intended, if instead of having something nice like this, essentially rectangle and triangle, even if you have something curvy. So here's again volume, here's again pressure, and maybe for some reason in the process that we're undertaking, we end up with an arrow like this. It's still okay to figure out the total work done by taking the area under this curve, but that's a little bit hard to do algebraically. And so the way that we might handle that is by approximating it with a series of rectangles. And so this right here, the rectangles I'm drawing here, will kind of overestimate the work done, but you can draw a second set of rectangles and get their area and underestimate it and then average the two. If you've done this on graph paper, then you can always just count how many squares on your grid are included within your area that's enclosed. So again, we can do area of all these little rectangles or grid squares or what have you, and once again, area equals work. That's all that I wanted to do in today's little video. This was meant to introduce this concept. We'll have another video to tie it into the first law of thermodynamics on another day. But in the meantime, thanks for watching, and I hope you learned something from it.